Let's go ahead and get started. You should be in or expecting ECE, Electrical and Computer Engineering, number 207. That's the class. If you're looking for global change, you can step outside. No, actually, it's in room 140, I have since learned. But this should be ECE 207 in ILC 150. I'm mic'd, and I'm also on another microphone. We're trying to record these lectures for distance learning purposes, meaning when you ask a question, they won't see your face, but they may not hear you either, and so I'm going to try to remember to repeat the question that you ask. If I fail to do that, please remind me, hey, I didn't hear the question. Please ask me or cue me to repeat questions that you might have as a class. What's being recorded is what's on the screen. There is no camera that I'm aware of recording us that way, but what you will be seeing if you watch this extremely exciting video would be the screen capture and hear the audio as it's being spoken. Formalities to get out of the way. I want you to sign in to attachment 2. I'm going to be passing around 3 pages. One page is attachment 1. If you want to add the class, sign attachment 1. If you think you're already in the class and it's on your schedule, sign attachment 2, and there will be 2 pages of attachment 2. Is that clear? Attachment 1 only if you want to add the class, and then we'll see if there's enough space. I thought this room, well, maybe we have more in the class than I was expecting, but that's maybe a good thing. If you try to find the class on D2L, you won't find it just yet. They're developing the website, but that's not the one that you have access to, and I was thinking, well, they'll probably get automatically inserted into this development one. It didn't happen. Yesterday, I believe I made the request, but before or until the D2L website becomes live, you need to go to the following website, and I can see if the lighting can be changed a little bit. Please don't fall asleep on me. Did that help at all? If you go to ece.arizona.edu/tilde and my last name, Tharp, T-H-A-R-P. So it's HARP with a T in front of it. The world according to, no, you weren't even born yet. The world according to GARP. Probably never heard of that. Anyway, it's not GARP, it's THARP. Let me see if I can write that down so that it's better for you. Here's the website. It's www.ece.arizona.edu. Now I can never remember. Is it that way or the other way? Guess I can check, but it's going to be way too slow. Okay, that was the correct direction. And on that particular home page, you should see a link to ECE 207. You can link to 207. On there, I've already posted the syllabus and the passport assignment. The passport assignment, I want you to turn in by Thursday. The passport assignment is really my way to try to learn all 150 names and associate those with a face. It's not good enough to just know the names, is it? I could call out a name and someone would respond, then you'd be impressed. But I probably won't learn everyone, but it's a good way for me to start to identify names and faces. This is the passport if you find the link. It's there as a PDF file. It's also there as a Word document. You can edit the Word document, fill in your name, tell me how you want that pronounced. If your given name is John Smith and you go by Peter, Peter is the nickname that I'm looking for. That's what you want to be called in class. Provide your email, the code number. How many people still have their clickers, or have you already sold those on Craigslist? Who still has a clicker? That's not 100% representation, is it? We may try to use the clickers, but it looks like that's not going to be that effective. That's why the code number is there. That's supposed to be a 4-digit number unique to you. Maybe you could use the last 4 digits of your phone number. I won't know the first 3, so I won't be calling you at 3 a.m. to remind you that your homework is due that day. That's not a bad idea, is it? You'd still be up. I'd have to write a program to do that because I wouldn't be up at 3 a.m. to make that call. But give me a 4-digit number, and don't be too creative and say 000 or 777 or something. That gets used quite a bit. Don't be James Bond. Use something that's maybe a little more unique. Otherwise, I'll have to go back and forth with saying, wait a minute, I have 10 of you with the same 4-digit number. 1111 may not be that unique. Does that make sense? Pick a number that you think might be unique to you. Hopefully we will not have too many adjustments. Provide a photograph, not your baby picture. I want to know what you look like now. I told an earlier class that I don't yet have the software to do the age progression, like on a milk carton, where you would be there as a 5-year-old and then they age progress you until you're 20 or whatever age you are now. Then provide a unique, interesting fact about you. That will help actually solidify this connection with the name and the face. What's somewhat unique to you? And that is, be creative. Somebody in the last class raised their hand and they said, if I eat pancakes with onions and ketchup, is that unique? I said, that's probably unique to you. No, they didn't ask that, but that would be unique, I think. Somebody said, what are pancakes? I said, that might be unique to you. No. What else? Learning style. There's a quiz online. I want you to provide me with the results of that quiz. It shouldn't take you very long to check through that quiz and identify your learning style based on the quiz. Then you can tell me whether you agree or don't agree with that particular quiz's assessment of your learning style. I'm trying to gauge how everyone in here learns, but is there a majority learning style? I might try to tweak my lectures to make that more effective, or really I'll probably try to make it varied so that I'll resonate with somebody all the time, hopefully, is the idea. What else do we have? Then I want you to read the academic code of conduct. Basically, do not cheat. The risk isn't worth it. The risk is too great of getting caught, and then now the penalty's too high. So just don't do that. It's better to just take a 0 on the assignment, even if that's the final exam, and that's true. Let's talk about the syllabus. That's also a link on that page. I'll try to put all of this on D2L when they give us the D2L site. That's my fault for not requesting the D2L site until yesterday. But we will try to make do with this one. Had to try to dust off my HTML skills to try to put this together. So if you can't link to something, or if you can't get access to that, send me an email. My email address is tharp@ece.arizona.edu, Office hours are the same time, just 2 different days. And it's not a Tuesday, Thursday, it's a Tuesday, Wednesday, so that if you do have a scheduling conflict on Tuesdays, hopefully you can make the Wednesday or vice versa. If none of those work and you have a question, send me an email and we'll try to come up, or see me after class and we'll try to set up a time that would work for that particular week or for that particular problem or question. I've listed, in anticipation of being given a D2L website, the D2L address. And I'm assuming everyone knows or has used D2L in the past, and we'll try to do that. If we get it quick enough, maybe you can do a Dropbox on your passport. How many have purchased a text? Do you remember what edition it was? Quiz. Put down your code and write, 4, is it the 4th edition? The 5th edition is now being sold, but I believe the bookstore, I was told at the first of summer, oh, you're using the 5th edition. I went to the bookstore 2 weeks ago and I looked on the shelf and it's the 4th edition. So we'll use the 4th edition. If you have the 5th edition, you may have some more features. I think oh, good. Here's the 4th edition. My Vanna White. People watching this video will not know what I'm doing, will they? You can play it and just laugh, right, when I talk about Vanna White. She's never this wet. I'm all washed up. 4th edition of the text is what we will use. Homeworks will come out of that. We'll try to have 10 of those during the semester. I hope that you're not frantically trying to complete your homework during class. I typically don't like to have it due at the end of class, but I thought you may be late that day or something may happen and you come in and you're not going to make it right at the start of class. I don't want to penalize you for that. If you sneak in, sit down quietly, and take notes the rest of the hour, then you can hand your homework in after class. If you want, you can hand it in before class. We'll just start a stack here, but don't come up during class and hand it in. Just wait until after class. I don't know if anybody has this classroom after us. Was this classroom in use before? Pardon? 45, so maybe there is a class they just dismissed early. You won't be so fortunate. We'll go the full 75 minutes. Maybe it'll be finished raining by then and I'll be dried out. Oh, examinations. We'll have 3 in-class exams, and the point totals for those are on maybe the 2nd page. And here are the tentative dates. We'll try to stick with those. September 21, October 21, and not November 21, but November 18th. The final exam is the 16th. I believe that's a Thursday, and it's from 2 to 4. If you think if there's an error in that final exam day or time, please let me know, but I think that's correct. You will miss 2 days of Thursdays. Darn. Veterans Day, the university is not in session, so you will not come on the 11th of November. And Thanksgiving, we won't meet. You would be all asleep anyway after a big Thanksgiving lunch once the turkey, tryptophan kicked in. Course outcomes. This is what I hope you're able to do by the end of the course. We won't go through those necessarily today, but you should, as you're preparing for exams and the final is planned to be comprehensive. This will probably be a pretty good indicator of what will be on the final exam in terms of question types. And you can see that they're not real specific. There are all sorts of resistive networks that I could create, but you should be comfortable solving resistive networks, solving first-order circuits. Hopefully everyone has the prerequisites for this class, which I think means concurrent registration in differential equations. Is that true? And you should have had the electricity and magnetism physics class. Is that 241? The fourth page of the syllabus is a chapter by chapter outline, essentially, of the material. And we're not necessarily going to go linearly through the book. We will start that way. We'll start in chapter 1. We'll move to chapter 2, 3, 4, 5. So it looks like it until we hit 5, and then we change a little. Then we jump into chapter 14. Then we jump all over the place. Chapter 9, chapter 10, chapter 15, 16, and 12 and 13. We're trying to get through the book. Most of it is the idea. Questions on the syllabus? I think I can still see, even though it's somewhat dark. Can you guys hear? And you can see the screen? Okay. Good. We've already talked about the passport. We've talked about the syllabus. Let's see what else is on tap. Let's look at the big picture view of electrical engineering terms, and we'll start working with Chapter 1 material. I may have a bad back at the end of this lecture, as low as this table is, but we'll make do. Hopefully we'll be able to write. There is. I was just afraid it might make too much noise or it'd take too long. What's the time constant on this system? We'll learn that in our first order circuit analysis. Oh, that's as high as it goes? Okay. Still be on one knee. They still can't see that in the audio or in the video, but that's better. Thank you for the suggestion. Where was I? Oh, before we get into what I did on my summer vacation, isn't that what you always do on the first day of class? Answer that question. Oh no, let's not do that just yet. Let's try to erase. Course overview. What do we really want to achieve? Or what are the objectives, overall objectives? First, and probably foremost, is this is on your academic program. And so you need to complete your program requirements. The main goal you have to help is to get you to pass this course. Okay, you have to pull your end. I'll try to do my part in helping you learn the material in order to pass the class. That's the number one objective. The other objective, let's say number 2, is how many of you plan to take the FE exam? Show of hands. How many civil engineers do we have in here? Or who's planning to take the Fundamental of Engineering exam? Or have you even heard of that? If you haven't heard of it, I don't expect you to raise your hand, but there's a few of you. We should give you enough information so that you can maybe not breeze through the electrical circuits aspect of the FE exam, but it shouldn't be too much of a problem after completing 207. The other course objective is to allow you to better understand the electrical aspects of the systems you will encounter in life and work. I want you to have a better gut feel for what's going on when somebody talks about some electrical system. You'll know a little bit more about what's going on with respect to power, energy, current, voltage, etc. Frequency. You'll feel more comfortable with those ideas and concepts at the end of this class. With that in mind, let's now look at the big picture. And you can see that as long as you can keep up with my writing, you're okay. I don't have a deck of 40 PowerPoint slides, and I'm not going to advance through those in a hurry. Hopefully there's some learning going on actually as you copy down as we work together. So what's the big picture view of electrical terms? To begin with, let's talk about power scales. And by that I actually do mean power, wattage. How many people have a cell phone? Probably a pretty high percentage. And the others, maybe you broke it in the rain coming to class. Don't have a cell phone. Good, good for you. Oh, how many? I forgot to repeat the question. You guys didn't tell me. So the question was, how many do not have a cell phone? Is that correct? Now I feel like Jay Leno or something up in the audience. This is kind of fun. What? I'm sorry? Okay. Come on down. Well, I'll get my exercise maybe. Power scales. Cell phones. Let's just assume in round numbers that a cell phone consumes 1 watt. They transmit, when they transmit, it may transmit at 600 milliwatts or 0.6 watts, or it may crank up and go to 3 watts. Let's just sort of take an average and say 1 watt for the mean load of a cell phone. 1 watt. So that's how much power a cell phone uses. Suppose that we now take 1,000 of those cell phones. Ten to the 3. Something that consumes, so now we have one kilowatt, something that you're hopefully familiar with, a hairdryer or a toaster consumes 1 kilowatt, 1,000 watts. That's 1,000 cell phones. How many are in here? In round numbers, if we had 200 here, it would be 5 groups this size with cell phones. That's 1 toaster. Toaster consumes quite a bit. In fact, this 1 kilowatt is the average typical home electricity demand. On average, a home just sitting there consumes 1 kilowatt, 24/7, 365 days a year. You can, in round numbers, think of a home equivalent to 1,000 cell phones. Well, this is not energy, is it? Good question. The question was 1 kilowatt for what length of time? So we're saying this is the average load. It consumes 1 kilowatt of power. So if you want to know the energy, then you define the time, and then you integrate that 1 kilowatt average, which we're assuming is flat, for the length of time. So if you said, okay, well, in an hour, well, you have 1 kilowatt hour. If you now get billed for that 1 kilowatt hour, in round numbers, that might be a dime. 10 cents is what you pay the electric company for that 1 kilowatt for 1 hour. So if you now have 24 hours, you now have 24 dimes, help me, $2.40 a day that you're paying for your electric bill. Does that sound about right? No, not in the summer, not in Tucson, right? Depends on how efficient you are. But TEP now sometimes guarantees $1 a day or something. That's pretty good for energy use. We'll get off that subject, but that's a good question. There's a difference between energy and power. One's the time integral of the other, or power is the derivative of energy, is another way of thinking of it. We're talking about now the power demands. 1 kilowatt, a toaster, or one home. What if we took 1,000 of those? Or 1,000 homes. That's now 1,000, or 10 to the 6 watts, which is 1 megawatt. And that's a capital M, not a lowercase m. A lowercase m would be 1 milliwatt, which is 10 to the minus 3. Mega is 10 to the 6, go figure. But so the m and the capital M are not reciprocally related. What is this? Well, this is roughly, I know we have some of you in here, this is basically one small jet engine. 1,000 homes is what the power demands of one small jet engine. So if you had 1,000 homes, the average power load or demand is the equivalent, roughly, of one jet engine, what it would consume if it was on 24/7, 365 days a year. But it's going to have 1 megawatt. So if somebody starts talking about megawatts, now you go, oh, that's a jet. If they talk about kilowatts, 300, you go, oh, that's like 300 homes, or that's like 300 toasters, or that's 300 hair dryers. If you go home and dry your hair, or your shirt, or your pants, or whatever, after this rain, hailstorm, wasn't it? Whew, I got hit. Probably be bruised. Kind of dainty. Sorry. I'm recording this. Sorry. Oh, well. Where were we? One small jet engine. I thought I was at 300 homes. Okay. 1,000 homes is one small jet engine. You see the pattern here. What if we took 1,000 jets? That's now 10 to the 3 times 10 to the 6, which is 10 to the 9th watts. or that's 1 gigawatt and what's that? That's basically a nuclear power plant. So this is the electrical output rate. So that's the power of a typical or a typically sized nuclear power plant. And I don't know what the Palo Verde nuclear power plant generates, but hopefully it's in that ballpark. You can report that back to me, or you can put that on your passport somewhere. Show me that you were actually listening in class, right? Okay, what's the pattern? How about if we take 1,000 nuclear power plants? That's a big number. That's now 10 to the 12th, which is 1 trillion watts. Or that's 1 terawatt. Or 1 TW. What consumes that much? Question? Oh. Didn't expect that. You were going to, I don't even remember the question. What was the question? What consumes 1 terawatt? Please.
I think that the entire Earth consumes 15 terawatts.
Okay, so the response was the Earth consumes about 15 terawatts. The global demand, the human demand of energy, what is the human demand is 15 times that. This might be this might be actually the global demand, let's just say, of electricity, but that's not the total energy demand, is it? But this might be the global demand of electricity. If you are so fortunate to be flying above the Earth and you see all these lights twinkling, the electricity that is requiring is 1 terawatt. But that's not all. We don't just do electrical to get our energy demand or our energy needs met. The article that I'm using to sort of get me through this, has anyone heard of Nathan Lewis from Caltech? These numbers, to just give us something to think about if you're doing a design or if somebody's talking. This is from an article or a lecture that he gave called Powering the Planet. And now we know something a little bit more about power demands. In that particular talk, he said that the actual demand of, let's say, the thermal load of human is about 13 terawatts, but this is an older lecture. So we're in the same ballpark. We're in the same order of magnitude. 13 or 15 terawatts. That's the global demand. And that's your challenge as engineers when you graduate, or as an intern even, is solving this particular problem. Can we, or maybe I should say, can you sustainably produce enough energy to meet this 13 terawatt power demand. And that's how much power is being requested or demanded all the time. 13 terawatts. Question? That would probably go up. Oh, I'm sorry. The question was, would that go up as the population increased? And yes, it will. So one way to maybe reduce that is to lower the population, the global population. Who wants to volunteer to solve that problem?
You ever heard of the Mott's proposal?
No. Okay. So that's the global demand. If you looked at what, well, in the paper they said the U.S. demand was a large fraction of that, 3.2 terawatts. Almost a third of that global demand is us, or we, in the United States. And if you divide that out, how many are there of us? Did anyone look at the most recent census? Was anybody a census worker this summer? Did you go door to door? How much?
310 million.
Oh, that's close enough. So let's say it's 3.2 terawatts. Let's say that's 3.2, well, let's say, let me not do it just yet. Erase, please.
Turn it into a comma.
You'll see my patience wear thin occasionally. Now I probably can't put the pen back on, but 320 million people, let's say, in the United States. So that's now 3.2 times 10 to the, what was it, 12 for tera. This is 3.2 times 10 to the 8th. So that's 1 times 10 to the 4th. Or that's 1 times 10 kilowatts. That's what it's claiming that we are demanding 24/7. 10 toasters to sustain us. Your job is to make that happen. That's why it's important to start learning some of these ideas and concepts in ECE 207. You had no idea this class was going to be that interesting, huh? You're going to solve the world's problems. Hopefully. That's power. What else can we talk about on sort of the big picture? You've probably heard more than just the phrase watts. How about amperes? There's two quantities that make up watts, and that's current and voltage. Current is measured in amps or amperes. Volts are given the unit voltage, typically. Now, in terms of scales, how do I want to do this? Suppose that we talk about a nerve cell in the brain. And we have this line, which we'll use a logarithmic scale because this is going to span a large distance. 10 to the minus 12 in terms of units for amps for the current going through, and amps are coulombs per second. In terms of units, that's one quantity. That's sort of the low end of the extreme. Has anyone been shocked before? Not real pleasant, is it? Well, I better not say. anymore. 10 to the minus 2. That's the threshold of sensation. Maybe I should quantify that as humans. So if you grabbed something, you could feel the tingle at 10 to the minus 2, which is what? That 10 milliamps. That's when you can start to feel it. Doesn't take much more than that for you to quit your heart. That's why you don't really want to be holding on to wire with current going through it. And it depends, obviously, on frequency. If it's high frequency, it's not quite as bad as low frequency or direct. But typically, if you're in a lab, you keep one hand in your pocket if you're going to be touching or looking at something. You don't want to be grabbing two things and allow that current to go right through your chest. You just want to sort of look. That's what I learned as a TA for labs. Especially, you don't know what they're building necessarily or what they've put into that circuit. You don't want to be grabbing things with both hands necessarily. It doesn't take much. They've even done experiments a few years ago, a few generations ago or decades ago. They paid, I think, UC Berkeley students to grab, and then they would ask, when can you let go? And there is a point where your muscles tense up and you can't let go. That's a very dangerous condition to be in. It contracts your muscles and you cannot let go. So what do you do if your neighbor is doing that? You don't want to go up and hug him because you'll be doing that. So you want to somehow get some non-conductive material, a board, something, get him away from that condition to save him. Hopefully you won't have to do that. All right, 10 milliamps, that's what we can feel. And it's not much more for your heart to stop. What are some typical household currents? Probably in the 1 amp range. Household appliance. Did anybody see any lightning on the way to class? Really? It was lightning? Oh, that's 10 to the 4th. That's pretty good size. Again, that's current or amperes. And that's part of this piece that the product of current and voltage gives us watts. In terms of voltage, some ranges to think of. Oh, and this probably isn't in your book, these particular numbers and this discussion, that now that I've already gone through it and almost finishing, start taking notes. For a radio receiver antenna, that can pick up very faint voltage levels, 10 to the minus 8. Has anybody had an EKG? An electrocardiogram, where they stick these things all over you and then they say, relax. Sure. What's going across your chest? Levels that are, let's say, roughly 10 to the minus 3 volts. Not much, actually. How about a flashlight battery? 1.5 volts, depending on the number of cells that you have and the bulbs that are there. car battery, 12 volts, right? What's house wiring? 120 typically out of the wall. So let's say 10 to the 2 or 100. If you're around campus, a lot of or in our building, the electrical and computer engineering building, the lighting, it's not 120. It's 277. Go figure. Maybe we'll talk about that. That's sort of three-phase, line to neutral, line to line, that kind of thing is how you can come up with 277 volts for building lighting. What are some others? Wow, I can't even read this anymore. How about if we go to lightning? 10 to the 8th. We've talked about power, which is the product of volts and current. Let's talk about one more thing, which is frequency. Again, this is the big picture, getting you thinking about these quantities, the different variations on those. What's the frequency of the electricity coming out of the wall? 60 hertz. If that was applied to something that could resonate, could you hear that? Could you hear 60 hertz? If something was vibrating at 60 hertz, could you hear it? Depends on your ears, I guess. Where am I? Somewhere between 1 and 100. Let's say this is 60 hertz. And hertz is cycles per second. Ideally, if you have young ears, good ears, 20 hertz to 20,000 hertz is what you can hear. Was anybody ever here in the lab when I was doing that for Summer Engineering Academy, where I would actually test your hearing? Turn on a function generator and put it through a speaker, and we would sweep it through the different frequencies. The speaker that I had probably actually couldn't resonate at 20 hertz, but that's pretty low. That's what you hear going up and down Speedway with the big loud woofers in cars. The real low frequencies would be in the 60 hertz, 40 hertz range. What's middle C? Musicians. I don't remember. That's why I was asking. It's somewhere. We'll check. That could be on your passport too. What's the frequency of middle C? And then you can come up and sing it. See if you can hit a pure middle C, a pure tone for the frequency. That's then above 100 hertz, isn't it? Let's say our voice is probably in this range of 200 to 800 hertz, probably. So let's just say there's 1,000. The human voice is in there somewhere. On American Idol, if you're watching that show and you have a frequency, you capture the frequency content of those people singing, that's where you would see your frequency coming in. What about some different radio signals? How about the AM radio? Wow, this is terrible. If you look on your dial, then in terms of television stations, have you seen these acronyms? VHF, very high frequency, and UHF, ultra high frequency. Those are in the 10 to the 8th, roughly. I'm running out of line. But if we keep going, how about microwaves? That's, let's say, between 10 to the 10th and 10 to the 12th. That was a 2. How about X-rays? 10 to the 18th. Gamma rays, even higher than X-rays, more damaging. Those could go all the way up to 10 to the 22nd. That's high. 10 to the 22nd times a 10 to the 22nd times a second. That's fast. That gives you somewhat of a big picture of electrical quantities. Talked about power. Your home is a toaster. 1,000 cell phones. Or you have 1,000 toasters, what's that? Jet engine. 1,000 jets. A nuclear power plant. And what is a jet? Is that about a megawatt? Did anybody go on a summer vacation this year? Did you see any windmills? Those actually might produce about 1 megawatt, maybe. And that's enough for 1,000 homes? So we have to have a lot of windmills to power the United States. All right, let's move on. Now let's get into chapter 1. And as we do that, let's talk a little bit about basic quantities. And about as basic as you can get is charge. What you can do tonight, go home, blow up a balloon, rub it on your shirt, stick it on a wall. It's charged. Or get some tape, put it on a surface. Now you can see if you can make positive and negative charges. But now we have charge, both positive and negative. There's only two. There's not a middle charge. There's just one or the other. And we've come to call them positive and negative. The unit on this charge is a coulomb. If you have a lot of charge streaming or moving, that's what gives us our current. And that's coulombs per second, or amperes. If you have charge that's separated, then that is voltage. Which is how much energy does it take to separate charge? Joules per coulomb, or volts. And the product of those two, as we said before, is what's needed when you have your cell phone to make it work. It might have a battery. That battery is so many volts, and then it consumes so much current per unit time. And you might look on the battery, and it might say 800 milliamp hours, and that would tell you how much energy is stored in that fully charged battery. You're assuming it's so many volts, maybe 3.7 volts. Your ability to make technology so that you can store energy in a smaller and smaller place allows us to shrink and shrink all these cell phones. How many have a cell phone that's 10 years old? Don't see too many hands, but it's maybe bigger than your neighbor's who has a brand new cell phone. And a lot of that is the shrinking electronics and the shrinking battery. The ability to store that energy in a smaller and smaller space. We had this pointed out in a question earlier, but if we wanted to talk about energy, that's the integral of this power, or the time interval over which this power is being demanded or requested or asked for. And to give us a feel for size, maybe, an electron is minus 1.6 times 10 to the minus 19 coulombs. That's how much charge it has or possesses. And if we wanted to see how many electrons it would take to actually contribute or create a charge of 1 coulomb, if we're dealing with electrons, that will be minus 1 coulomb. We can just do the math, and the number of electrons is 6.25 times 10 to the 18th. So 1 coulomb is a large amount of charge, is the idea or the notion. Let's look at a very basic circuit. Suppose that somebody draws the following schematic. Does anybody recognize what that might be? Okay, I heard some. I just like walking up and down the stairs. I'm sorry. This is fun. That on the left, I had to do this so that I could get your perspective. But on the left is a battery. Those lines, those straight horizontal lines, that's a battery or a voltage supply or a voltage source, which typically we label. The longer lines are the positive side, the smaller lines are the negative. We may give it a value V sub S, and we might say, oh, that's a 9-volt battery, which they've provided if the microphones run out of power up here. Then we have a replacement battery to put in, to install. I think I heard that somebody said this was a diode, and that's correct. This entire circuit, you could say, is an LED driver circuit. You could go to Radio Shack tonight on your way home, buy these parts and build this circuit, and you'd have an LED that you could light up. Your roommate would go, what in the world are you doing? You'd say, well, do you recognize what's on the table? No. It's an LED driver circuit. That might be kind of fun. Okay. It's all relative, right? What's fun to one person may not be fun to another. But that's a light-emitting diode, let's say. That's what the LED stands for. That should be maybe better drawn as a resistor, that jagged line, and that's designed to resist current flow, because if you just hook a diode up to a battery, you may burn up your diode, or it may not even do anything. It might beep, flash, it might pop, depending on the size of your voltage source. That's why you have that resistor there, to resist current flow or impede the flow of current. Typically, these diodes have a particular voltage associated with them. They operate at a given drop in voltage. Analogies, if you think of a waterfall, voltage is like the height of that waterfall. And the flow of water, the amount of water coming down, would be like the current. So you could have a really tall, a lot of potential, voltage you have as potential difference, potential. You could have a lot of potential and very little current, very small stream. Or you could have very large potential and a lot of current. And you can see that if you're standing underneath that, which we were just about an hour ago outside, we had a waterfall. Actually, it's called rain and hail. I didn't swear. Never mind. Where was I? Oh yeah, my waterfall. It would make a difference whether it was a lot of current, big stream, how high it was, a big potential, a lot of voltage. If you had a big combination, you have a lot of power. Maybe enough for a toaster to power your house. That would be 1 kilowatt. Where was I? Diode, voltage. It also, okay, it needs two things to work. It needs potential difference, needs that elevator, needs the waterfall height, and it also needs some water flowing over it to make that work. It needs some voltage and it needs some current. Typically, to light an LED, it varies, but you might be told that this particular light-emitting diode, you may want, so right now, all I have indicated are voltage drops. And if you look at this particular circuit, if you start down here and work your way around, you would sort of say, oh, the voltage goes up big, and let's say that, well, it actually just goes straight up. So let's say this was V sub S, that's now the height. Then you have some drop across that diode, and then let's say you have some more drop across that resistor, and you get back to where you started. And all we've shown right now is this potential, the battery potential, how much voltage there is across those terminals, and then you drop that voltage down, some across the diode and some across the resistor. As you're well, in addition to that, you also have some current flowing. So how much water is coming down from that waterfall? That's the current. So you have the height of the waterfall, that's V sub S, that's your battery, and you have how many electrons are flowing. What's the charge coming out of that battery? That's the current. For an LED, you may want this current I to equal 20 milliamps to give you a nice red glow or whatever color it is. Typically in the past they were always red. Now you've got all sorts of LEDs that you can have. But it might be that, oh, for this particular LED it might be really efficient, maybe it only needs 10 milliamps of current flowing through it to illuminate it, to make it look bright. What you don't want to do, if the LED says, oh, 20 milliamps, you don't want to be throwing 50 milliamps through it. It'll probably not last very long, or it may burn up right away. this, another way of writing 20 milliamps, is 20 times 10 to the minus 3, or 0.02 amps. We want to now design this circuit. We're now already worrying about circuit design with this one simple circuit that you're going to build from Radio Shack parts. You need to get a battery. Maybe you want to go to Walmart to get the battery. It might be too expensive at Radio Shack. Sorry. Then you get an LED and you get a resistor. If you sneak over to the electrical and computer, don't tell them I said this. A lot of times we have trays of resistors on some floor. You could maybe find a resistor. You wouldn't have to pay for that resistor. Then all you'd have to do is buy an LED at Radio Shack, maybe $1. Then you can impress your roommate when you get home. Tell them not to touch that LED. All right, where were we? Oh, we need to now figure out what's the size of that resistor you're trying to find, or pick the size of that resistor so that 20 milliamps of current flows in that given circuit. This way of analyzing the circuit, we can walk our way around in that black dashed line and essentially write the voltages that we experience or see as we move our way around that circuit. And we'll learn that that's Kirchhoff's voltage law, that we're going around this circuit, and the algebraic sum of those drops, in this sense, in this case, we are saying a voltage drop is positive. If we go from the negative side to the positive side of that battery, it's no longer a drop, it's actually a rise. And in that sense, we then experience a minus V sub S. It's a negative drop. It's a rise. We have minus V sub S. The easy way to do this is if you've labeled the circuit, you simply indicate the sign or the polarity that you see as you're moving around or walking around that circuit. In this case, we have minus V sub S. Then we have a voltage drop across the diode, plus V sub D, plus the drop across the resistor. And because we're not creating energy, we have this summing, algebraic sum, equaling 0. That tells us the relationship on our voltages for that circuit. We have, for each of these devices, a relationship between voltage and current that those devices satisfy. For a resistor, the voltage drop is proportional to the current flowing through that, and the proportionality constant is the resistor itself, the resistor value. It's Ri. So V is equal to Ri. That's the current. I'm going to have to quit making mistakes because my eraser's not wanting to work. That's the current voltage relationship of a resistor. V is equal to Ri. And you need to know that, memorize that in terms of a circuit. Here's our resistor, here's the voltage drop, and here's the current I. It's passive sign convention. Current's going in the positive side of the way that we've labeled that resistor. We now know that we can replace V sub R with R times I. And we already know what we want I to equal. And we're trying to solve for R. And V sub D is a given. You go to Radio Shack and somebody says, oh, here's a red LED, and you go, okay, what's its voltage? They might say, oh, it's 3 volts. So it likes to work at 3 volts. It has a voltage drop of 3 volts across it. We won't use that particular voltage, but we can now say V sub S plus V sub D plus R times I is equal to 0. We're trying to find what resistor do we want so that we can pretty accurately determine that we want 20 milliamps flowing through that diode. And we'll be given a particular battery. Maybe it's a 9-volt battery. But we can solve this equation for R. If we do that, we can take V sub S to the other side and V sub D to the other side and divide by I. That's simply algebra. And if we pick some typical numbers, suppose we did have a 9-volt battery. V sub S is 9. And maybe the diode voltage, the forward voltage on that diode is 1.7 volts. Question?
So just to make sure the direction you had was drawn, that's the direction you're talking about in terms of the signs, right?
Yes. So the question was the way that I had the signs drawn, and I'm hopefully being consistent, in this particular circuit, the way I have my polarity labeled and the way that my current is flowing, that's the passive sign convention. I'm absorbing power in that resistor. And I'm also using power to light up that diode. That power is coming from the battery, V sub S. And the current, the positive current, is coming out of the positive terminal of the battery. That's saying, oh, you're delivering power to the rest of the circuit. If it came up that the current was negative, then you're actually charging that battery, not discharging it. But you're discharging, you're pulling charge out of that battery to drive, to illuminate that LED, to light it. To light that LED, you want so much current flowing, and we said, okay, for this example, we're going to assume that that's 20 milliamps or 0.02 amps for the current. We're given then that we're starting with a 9-volt battery. The forward voltage on that particular LED that we found is 1.7 volts, and the current to make that glow nicely is 20 milliamps. This now says, if we do the math, we have 7.3. 0.02 is 2 over 100. That's my way of thinking. So that we now have 7,300 divided by 2, or 3,650 ohms for our resistor. That means we would need to find a 3.6 k ohm resistor and use that in combination with this diode and the 9-volt battery, and we would have a circuit that would light up an LED and it would do it effectively. And you wouldn't burn out the LED. Obviously, the battery is not going to sit there and keep that LED lit forever. It only has so much charge in it. And does it even tell me? No. Doesn't tell me how many milliamp hours of charge I could draw out of that 9-volt battery. But if it did, then we could tell how long we could keep that LED lit. I apparently see that the clock is reaching the witching hour by everyone's action. You think this is a convenient stopping spot? Did everyone sign the attachment? Attachment 2. Please make sure you sign that before you leave. If you have that, you might come up. There should be 2 of those. You can come up and then make sure you sign one of those. You don't have to sign both, just sign one. I'll see you on Thursday.